So today I'm joined by Richard Holub, the founder of HDR Associates, and we're going to be doing a bit of a deep dive into LFP cathode, specifically the most up-to-date LFP cathode, so-called Generation 4, what that means for supply chains, what that means for investment both inside and outside of China, and some of the key concepts that OEMs and other members of the supply chain are going to have to look at, and indeed why you're probably going to be hearing the term lithium dihydrogen phosphate a lot more going forward, as a potential product, as opposed to battery grade carbonates and hydroxides. So before we get into that, Richard, if you'd like to give a quick introduction to yourself and the company.
Sure. Thank you, Andy. Yeah, I'm Richard Holub. I've recently retired and started HDR Associates, retired from Albemarle Corporation after 35 years, I think. Yeah, I'm really just been, since meeting Andy at the conference in June, I've been collaborating with him a bit on the non-lithium part of the supply chain, the iron phosphates and other phosphates and irons to make LFP. So yeah, it's been quite interesting. He's been a great mentor for me, and I want to thank him very much for helping me out as I go along learning more about this supply chain. Thanks, Andy, and thank you everyone for joining.
Oh, thanks a lot, Richard. So say what we're going to start off with, I'll give a few sort of background slides as to where we are, and some of the challenges, particularly facing European and North American consumers of material. Talk a little bit about the calculus that they currently have between investing in a domestic supply chain or relying upon import material. And then Richard's going to go into more detail, looking at Gen 3 versus Gen 4, what makes sense for different parts of the supply chain, and also some of the implications around raw materials, and some of the patents, which could be throwing curveballs our way. So to start with, most of you will be familiar with this type of chart, which really just shows what China's current dominance is across the supply chain. When it comes to raw materials, China's involvement is typically a lot higher than is shown here via ownership. This is just looking at what's available domestically. And you can see there's a big difference between the raw material side of the market and that processing side. It's the processing side that we're talking about today. Why is that important to those of you invested in the mining space? Well, this is effectively where you're shipping your material to. And what we're seeing and what we'll see in the coming slides is that while you may be getting a lot more production of raw materials coming out of places like the US, Canada, Australia, and Europe, if there's no place to process them, you're going to have to ship those materials to China. And that obviously really defeats the point. And it's something that we've seen quite clearly in the rare earths market recently, where effectively, you can produce these materials, but if you can't process them, you're still very reliant upon that single point of failure in China. Now, when we look specifically at the cathode active material part of the supply chain, you can see here that the view that we have with China going forward, when we do a bottom-up analysis here, where we track hundreds of different cathode plants and operations and plans all around the world, is that by 2030, we still expect China to have about 78% control of that supply chain. Now, by control here, we mean ownership. And this is important because with cathode active materials, it's not just the raw material, you also have an intellectual property barrier there. Because this is probably the most important material when it comes to the energy density and the charging performance of a battery cell, and therefore obviously its performance in a vehicle or an energy storage system. And you can see that globally China maintains about 78% based on currently announced and risk-adjusted figures. North America, that drops to zero, largely because current rules don't allow Chinese investment to have any type of tax credit, and very difficult for Chinese companies to invest directly into the USA at the moment, and very difficult to invest into Canada because the natural market there is the USA, and we still have a lot of tariff uncertainty. Europe's a little more interesting. Obviously, that's where BASF and Umicore are headquartered. Both have pulled back a little bit globally. on their cathode ambitions, but still have facilities, up and running or being built in Europe. And we've also seen, a bit more openness in Europe towards Chinese investment. So you see that close enough 50-50 split there. Other entrants which are quite interesting is obviously Morocco. We've seen a huge amount of investment happening in Morocco. It's really one of the success stories at the moment. And interestingly enough, they have a free trade agreement with the USA, and they also managed to get a lot of financing from Europe. So Morocco actually sort of playing the sort of linchpin between Europe and North America very well there when it comes to supply chains. But as you see on the cathode side, that's very much Chinese controlled. South Korea, sometimes seen as being a bit of a backdoor, but to be honest, the vast majority of their cathode production going forward will be fully domestic and therefore sort of compliant with non-Chinese mandates in the supply chain. And another interesting one to point out there would be Indonesia, where obviously you have a huge amount of nickel laterite ore now being processed, and value add to produce cathode active materials within Indonesia, both for the domestic market and for the Chinese market. So when it comes to cathode choice, obviously there's the two main groups are ternary cathodes, typically NCM or NCA mixes, and then you've got your LFP type cathodes. We group those together here, and you can see our view as to how that's likely to develop. Now, what you had over the past 10 years was this big sort of run up in NCM type cathodes, particularly high nickel, and single crystal mid nickel cathodes from increasing the amount of nickel that you have, reducing the amount of cobalt as thermal stability management got better. And really, what was happening there is people were designing these batteries for a performance basis. And that's because they were very worried about range anxiety and charging anxiety. That was seen as a number one barrier to entry. Now, in China, that's slightly different. And in China, we've seen this huge explosion in LFP, where LFP is taking up, 70 or 80% of the domestic market at the moment. And I think a lot of forecasters sort of view that that will follow on in the rest of the world. And that's really not our view at all, from what we're seeing, both from current investments and in terms of just the calculus that you're making in selling into the automotive market, in Europe and North America. And you can see, on the bullet points there, which I just sort of quickly noted down, some of the main reasons that the US and EU transportation markets are very different to those in China. We don't have any battery swapping infrastructure to speak of, whereas many Chinese cities do. With a much lower population density in North America, you don't have the high-speed rail network that China does. Charging infrastructure is typically much more dispersed, much less units per number of vehicles, and also typically a lot slower. And that's not something which is going to change in 5 to 10 years. When you look at the amount of investment that's needed in grids, when you look at the issues with putting new charging stations up, it's very, very different, in China to Europe and North America. So again, I think from our view, you're going to have a lot more positive business case for NCM in Europe and North America than you do in China. You have bigger batteries, you typically higher sticker prices for vehicles, which allows you to have slightly more money invested into the raw materials for the battery, and you have worse infrastructure for charging. So again, it makes sense for more people to invest there. And again, you've more people with not living in flats to have access to home charging as well. So again, it can make more sense to have some more slower home charging than needing to go out and use a charging station like you'd use a gas or petrol station at the moment. That said, LFP will continue to make market share or to take market share in these markets. Most of the OEMs that we speak to, I think we probably speak to all of them, have decided upon some type of NCM and some type of LFP, as their core mix. So, how that splits out also depends a little bit on how you're splitting out between battery electric vehicles and plug-in hybrids as well. The other category there, just to say that that does include sodium ion. We do see sodium ion taking market share generally in the ESS sector and some niche transportation applications, but obviously those market splits hide a very high growth rate. So we've shown this chart before, which just shows the sort of the top line there is effectively the battery production level that we forecast in Europe and North America. So both of those going up to around or above 1 terawatt hour over the coming years. And you can see there that effectively both markets continue to be heavily import dependent for cathode active material. In Europe, a lot of that's coming from China, and in North America, a lot of that's coming from South Korea. And to be honest, a lot of it in North America will have to come from China unless we see more investment domestically, because it's going to be very difficult to fill that gap. And you can also, consider that the import tariffs there are going to weigh on any materials going into the USA. The shaded section there is on PCAM. So again, showing that there's even more of an import reliance when we start looking at the raw materials, the immediate precursors for the cathode active material as well. And it's worth pointing out that under the most recent sort of budget reconciliation, the so-called Big Beautiful Bill, the foreign entity of concern requirements for effectively access to Chinese firms into the US market and getting those maintained 45x tax credits means that US firms can license the technology, but there are a lot of rules there about how much ownership they get, how long they can pay royalties for, and in fact all of that guidance isn't even set yet. There's a mandate for the secretary to make further recommendations within a year's time. And again, it sort of makes it very difficult to make an investment decision given that level of uncertainty, both around tariffs and around how you can actually negotiate a technology swap deal. And that will lead us sort of quite well into some of the topics that Richard's going to be addressing in the slides coming up. Again, just looking at the PCAM side here, you can see that import dependence very, very high. Good example here in Europe of all the possible projects, probable projects, etc. But even with all of those, you're really relying on imports coming from Asia. So the big question, final slide from me before I hand over to you, Richard, is looking at the big question that this means. Do we buy or do we build for your cathode materials? And obviously that means are your lithium, your nickel, your cobalt, your phosphates, etc., being sent to Europe or sent to Asia? Typically, when we've modeled this and looking specifically at LFP, China has about a 25% advantage in terms of production cost. And that comes from, lower capex, easier to source raw materials, typically less risk and lower engineering costs, a bit more expertise in the supply chain. Those 25% can, to be honest, be largely offset by shipping and import duties. You don't necessarily need a full 25% import duty to have parity there. One of the big issues, though, is margin. This is an industry that's in huge oversupply at the moment. So typically what's happening is a lot of the Chinese cathode producers are operating at zero or even a negative margin just to stay in business. And, they suspended their debt payments or they're fully depreciated. Whereas if you're trying to set something up in Europe and you want to, or you're North America and you want to make a return on capital, that's very difficult to do when you're already facing a production cost disadvantage and then saying, actually, I also want to make a 20% margin on this. So I say the big sort of challenges at the moment, the big things that people are thinking about, how do we square the circle of making a margin and having a higher production cost? Can we rely on import tariffs and government support, given how volatile these have been, particularly with North America's tariff negotiations over the past few months. You then have a lot of IP risk. What if this product isn't as good as what we're seeing coming from China? And we'll talk a little bit about Gen 3 versus Gen 4 LFP energy densities, tap densities going forward. And then you've also got a little bit of policy uncertainty creeping in, as a lot of the OEMs are now trying to push back on the political mandates to end internal combustion sales or PHEV sales. So a little bit of background there from me. And Richard, I will pass over to you now to introduce us to Gen 4 and what it means for supply chains.
Thank you, Andy. Yeah, but before I dive into that, I'll just mention my perspective on things is process technology transfer, and process technology commercialization. So before I discuss this, just realize that's how I'm coming at it. Been doing that for a lot of years, and both into China as well as from China, quite a bit of it. So, okay, so what is Gen 4 LFP CAM? The distinguishing characteristics is the compaction, high pressure compaction density, greater than 2.6 grams per cc of the powder. This was in April 2024. CATL announced that it was the start of their Gen 4 LFP CAM. That really built on top of the January announcement by the Chinese government of the technology transfer limitations or restrictions. Just mentioning that CATL also meant a lot of the improvements over the years in terms of both compaction density from 2.3 up to 2.5, which are those three grades from 2.3, 2.4, and 2.5 are sold in China. But there's also a lot of improvement, as I'm sure the folks on the line are very familiar with, in terms of the cell pack design and other things. So what did CATL mention as the key thing for their Gen 4 raw material was mainly around the iron phosphate raw material. They mentioned particle size, and size distribution and shape as being critical to their technology to make the Gen 4 material. Their technology, as I go forward, we'll discuss that as the iron phosphate route. It's a solid phase synthesis route. The other route that's out in the being published and being discussed is called another solid phase route, the iron oxalate route, which is also achieving the Gen 4 compaction densities. Well, what is compaction density? Quite simply, it's a small amount of powder is put into a press cylinder, almost like a tablet press, and force is applied, and you measure for the amount of weight, the amount of volume at the end of the pressure being applied, and that gives you calculated compaction density. There are a variety of vendors providing this kind of equipment out there. If you wanted to do some work on your in development work, this equipment's readily available. Why is size important? The little graphic on the right just indicates that, for a packed bed of spheres, very uniform spheres, usually you're at around 38 to 40% void volume. And to get that being lower, void volume being air space that's not being useful for storing energy, to get that lower, you've got to go to a mixture of particle sizes to fill in those little gaps and also provide you the higher density we're going for. So that's just a representative graphic to give you a visualization of what we're talking about here. Next slide, Andy. This slide is really emphasizing 2 points. One is your final calendaring machine has to be able to achieve the roller press has to achieve the same kind of compaction densities, compaction pressures as the little tablet press I mentioned. So this is not completely independent of your choice of the equipment and capabilities of your calendaring machine. So make that point right off the bat. But also the XY diagram there is meant to emphasize that this Gen 4 is only one step in a progression. Knowing the single crystal density LFP of around 3.5 grams a cc, and that there's about a little over 1% carbon in there. Little bit of arithmetic, you can put together a chart saying, okay, well, what's the void volume versus the compacted density? And what this says is going from 2.5 up to 2.7, see the improvement from around 28% void volume down to say 23% void volume. So a 5% decrease in void volume, about a 20% of that is improvement there. So, but also says, there are quite a few examples of part of these types of things being at void volumes of 10 to 15%. So it says there's quite a bit of room for improvement into the upper, maybe other generations. In fact, you'll see some press releases mentioning Gen 5 material now, although it's very early stage. Really only Gen 4 material is well defined and is being commercialized today. Next slide, Andy. Thank you. So what is the export restrictions in China? In January of this year, they first came out for comment. They were implemented, I believe it was March. And then there was a recent update in July. But those export restrictions for LFP give you a pretty good idea of what not only the Chinese government, but also the producers of this material in China think are the key things that define this Gen 4 material. Now, this is a direct translation with some red numbers that are noted here, so I'll make a comment on those. But the formula really for LFP allows for a metal, I'll say M sub Z, an unspecified metal to be added. You might think that's manganese. However, there is a separate parallel restriction for lithium iron manganese, which also includes another metal, unspecified metal, in the full battery of technology restrictions. So it says the compaction density of the powder has to be greater than 2.58, a little bit more specific now, not the 2.6 you see in press releases. And also 220 megapascals of pressure are key things, and that it gives also a discharge capacity at effectively 0 degrees C and a recharge or Coulombic efficiency of initial of greater than 97%. So that's what, at least in the technology arena, what the folks in China believe are the critical things. And the next part of that restriction is around the iron phosphate cathode raw materials. And you see that there's a list of potential raw materials that are technology to produce these is being restricted. But they specifically call out that the iron phosphate would have the following conditions. All the discussion around particle size and those are all kind of summarized into a tap density here of greater than 1.2 grams per cc, and then also magnetic foreign matter of less than 10 parts per billion. A little typo here, but the numbers that have changed from January to the July output was the 220 megapascals was reduced from 300 megapascals, so that actually is now a more stringent requirement. And in the original version, the tap density of the iron phosphate being 1.2 grams per cc was actually listed as 2.1. I'm pretty sure that was just a switching of the numbers. But not necessarily a tighter restriction. And I'll mention that magnetic foreign matter is a very difficult thing to measure, especially in paramagnetic salts like iron phosphate. And the procedure for doing that is still not well defined, and I'll talk about that a little bit later. Next slide, please, Andy. All right, so you got these two routes for solid phase synthesis in China, the iron phosphate route and the iron oxalate route. The iron phosphate route is a carbothermal process, meaning that you've got to have, basically, it's like a mini version of a blast furnace. You're using some carbon source in order to reduce the iron from iron 3 to iron 2. It builds on, of course, the huge, all the Gen 4, 80% of the Gen less than 4, I'll use that term, LFP is made by this process in China, but it does add a second sintering step, and it has a lot of optimization of parameters across the entire production line. And I don't mention here, but also a lot of discussion about basically separating the particles and recombining them in order to get the right particle size distribution. Overall, this is going to be a low capital approach in China because you're building on top of an existing infrastructure for new capital. But it also requires a lot of technology development by your iron phosphate supplier to meet these requirements. And ultimately, at the end of all that, the highest numbers reported for this process being able to achieve are the 2.6 grams per cc. So that's just a little above the technology restriction of the 2.58. Now, the iron oxalate route is also solid synthesis, but this route was the first route to supply Gen 4 material in China in 2024. It overall appears to be a much more robust process and with less restrictions on the raw materials as the iron phosphate route. And it's also been reported to give compaction densities as high as 2.7 grams per cc. Not to say this is the only process development that's occurring both inside and outside of China. And these there are liquid phase synthesis routes, but you just don't see a lot of compaction density data at this point in time. Maybe that'll come. I will note that Diononics or Defang Nami, they recently published in a press release that their Gen 4 product by their sol gel liquid sol gel process is gaining some acceptance with customers in China. That's just a press release that came out recently on that. So there are other ways. I'm focusing on these two solid phase synthesis routes today. Next slide, please, Andy. So as mentioned, that the iron phosphate route builds upon the raw material sources that are already in place, but it does increase the requirements for the iron 3 phosphate. The iron 2 oxalate route uses the same raw materials. I will, as Andy mentioned, there's number 2 and 3 on that list can be combined into making the lithium dihydrogen phosphate, but ultimately it's the same raw materials and raw material supply chains as the iron oxalate route as the lower generations of product. Raw material, you can look at these raw materials. There are costs available in the SLM index. I use the numbers from August 21st. You run through that. If they're getting an equivalent yield to product, both on the iron and the lithium, that the difference in really puts the iron oxalate route at about a 400 RMB per ton disadvantage to the iron phosphate route. But as I mentioned earlier, the iron phosphate route has robustness issues as advertised. And one way to reflect that would be how much lower grade material would be made by the iron phosphate route versus the iron oxalate route. And how does that affect this technology decision? Next slide, please, Andy. So this is a simple sensitivity study on that, what I just mentioned, the yield to lower grade on the iron phosphate route. So across the x-axis there, that's how much of the lower grade you would be making by iron phosphate compared to on the y-axis is the iron oxalate route at 100% yield, let's say. So the 1400 RMB per ton disadvantage is shown there on the y-axis intercept. And as you go to the right for the 3 different grades that you can purchase in China from the index prices, you see that you can make up to 20% of the lowest grade there, or up to even 50% of the 2.5 grams per cc grade, and still not reach the break even of, and just reach, I'm sorry, the break even of a net. The choice of technology would be equivalent in both cases. So that's just a simple sensitivity study about how to look at this potential potential robustness problems of the iron phosphate route. What is that? As I said, this was assuming that everything other than that the raw material costs are the same. That's not necessarily true. The iron phosphate route does have an additional sintering step and higher costs, but an indicator of that is this LFP powder processing fee that's also available on SLM. And the differential between Gen 4 and the Gen 2.5, if you will, there was about 4,000 renminbi per ton. That would include profitability as well as this difference in production costs that we expect because of the second sintering step. And you might say that because right now that I'll say that the availability of people to process to Gen 4 seems to be very limited in China. So I'd expect that 4,000 to include quite a bit of profit if you're in a market shortage to do the processing. So it's going to be less. So the difference in cost is going to be less than 4,000 renminbi per ton is the point I'm making. All right. So at that point, you just say that, there's no real driving force from a robustness to the process in China where there's an established market for these lower grades. There's no real driving force not to choose the iron phosphate route. So if you go to the next slide, Andy, thank you. So basically, in China, still expect the iron phosphate route to dominate since for the points mentioned earlier. The iron oxalate route, because of reported advantages, might be, if you're building in new capital, might be a competitive choice to be considered. And Andy, you might want to comment on that. I think you had some information on those kinds of decisions.
Yeah, and it's worth pointing out, we talk a lot about, the Chinese industry just moving forward as this sort of juggernaut whereas everybody else is navel gazing at looking at their discounted cash flow models. Well, it's not entirely true. We have actually seen a big slowdown in the level of investment happening in Chinese cathode rollout. So that is having an impact. People aren't necessarily just running to build the next best thing and to triple their capacity anymore, given the massive oversupply that the industry looks to be in, at least for the next couple of years. That's certainly slowed down the rollout of LFMP, which I think about a year ago, a lot of people had their hopes up, saying, "Look, well, this is the obvious choice now." But actually, because that meant quite a bit of re-engineering, a lot of companies just stuck with LFP or have made the types of process improvements that Richard's been talking about to try and increase the density of that material. We've also then obviously seen the impact of lower lithium prices on the rollout of sodium ion as well. So a lot of pullback there, just because the actual financial considerations do impact China. They just impact in a slightly different way. Back to you, Richard.
Thank you. Now, for the rest of the world, as mentioned, right now we see no technology restrictions for Gen less than 4, using that term technology to be brought out of China to make LFP. That could change in the future, but right now I'm not aware of any. So then you have a decision to make in the rest of the world. If you want to do that, do you bring out the iron phosphate route? And that has, if you implement that technology, the requirements to change it to get to the Gen 4 are pretty substantial in terms of additional steps, et cetera, and raw material changes. Still ties you to the technology export restrictions quite tightly as you go forward for both the changes to the process as well as the supplying the raw materials to the process. The iron oxalate route is actually not as widely used in China, of course, but it has, from everything I've seen, it has a greater possibility to upgrade without licensing or purchasing raw materials in China. There's less raw material requirements, as I mentioned on the iron phosphate, and the upgrades to get to Gen 4 are not involving a lot of equipment changes. So it has a more robust process, potentially with more likelihood of separating yourself from a China supply chain in the future. Next slide, Andy. Yeah, I'll just quickly touch on relative to that on the Tesla patent that was published in January of this year. This is not a legal opinion, always a disclaimer, right? This is a process technical guy looking at it and saying, well, here's what I think. So simple summary, it's a process patent or utility patent in the terminology. It's involving solid phase synthesis, really, for I'll say almost every CAM formulation I'm aware of. And the key thing is they use a term called plurality, which has a different definition in intellectual property than it has in political terms. You can have a plurality of votes. That has a different meaning than in intellectual property. So you have to be careful of the language here. My simple description of that is they're requiring that no raw materials be completely dissolved in the processing steps. And that relates well to their announcements about this patent that revolve around a low cost. So if you don't dissolve the raw materials, you're going to use less solvent. And if you use less solvent, then you use less energy in the spray drying step. So it jives pretty well with the patent jives pretty well with the announcements they've made about the importance of this patent. The compaction density of the final products is not mentioned, only that the raw materials produced are CAM. In fact, there's no mention of the quality of the CAM. It could be the lowest quality CAM in the world, but they don't mention that at all, so it's covered. Process options there's over 100 pages of the patent, a lot of flow diagrams, a lot of options, takes a lot of work to dig through all that. I'll just summarize here that they're very broad. And final mention, as we mentioned, talking about bringing technology, buying technology, this will have to be part of your freedom to operate evaluation of any technology you're bringing out, which relates, of course, to many things. But of course, in the Western world, freedom to operate is a pretty critical thing for most companies, that you get the technology, you can run it without encumbrance of this patent. So I'll just mention that as a kind of a caution. And if you want to go to the next slide, I'll wrap up with one final caution. If you decide simply to buy Gen 4 LFP cathode material from China, The current China standards on these types of on these materials is not really caught up to the technology restrictions. Simple example is there in the middle about compaction density for cathode materials. The China standard, the GBT 44330 2024, so it's very recent. It's still it talks its requirement is a 10 megapascal pressure, and also that the density of the final powder be measured after you relieve the pressure. That is not in alignment with these technology restrictions, which specify 220 megapascals as a compaction pressure, and it also doesn't specify anything else in the technology parameters in the technology restriction. So no other parameters are mentioned. Now, there are a lot of companies who provide this kind of compaction density testing equipment. I list one here, IST, if someone wants to look it up. But there's one example given where this compaction density can go from 1.8 up to 2.5 grams per cc over the 10 to 200 megapascal range, and that you lose about 2.5% of your density when you relieve the pressure on the sample. So how do you set a specification? You're not going to be able to rely on a GB standard here. You're going to have to really dive into the details of the method as well as the specification in order to set a specification for a powder you want to buy. And then the last bullet is around the magnetic foreign matter, which I mentioned much earlier. You saw the 10 part per billion specification in the technology restrictions. But if you go to the GB standard around anhydrous iron phosphate, the actual standard lists 2,500 parts per billion, and also discusses how difficult it is to measure the magnetic metal material in a paramagnetic salt. So there's another example where you're going to have to dive very deeply into the methodology to set a specification if you want to buy iron phosphate from a China supplier. You're not going to be able to rely on the GB standards. With that, I'll wrap up. Turn back over to Andy to kind of close us out, I believe.
Yeah, thanks, Richard. And just a reminder to everybody, we do have that Q&A function, and I'll start going through those questions shortly. Just sort of one quick observation. I'm sort of guilty on a lot of the calls that I do of saying that OEMs are navel gazing. I think I said it earlier when it comes to their cathode choice and their investment choices in the supply chain. But to be honest, from what we've been talking through today, where you've got changing export restrictions on technology coming from China, and that can change every month. You've got changing tariffs and tariff regimes again pretty much every week at the moment. You have potential patent barriers, which again will cause more uncertainty. And indeed, you've got potentially changing electrification targets as well. So incredibly difficult decisions for investors to make, and all of that into a supply chain that at the moment doesn't really make a return on capital, despite the increased demand growth. So we often talk about the raw material positions, particularly in lithium, as being unsustainable. But I'd argue as well, the current position in PCAM and CAM is also unsustainable, given the demand growth that we're seeing. And that demand growth isn't just reliant upon electrification targets anymore. So very difficult to make the right decisions. And that's, one of the reasons we do these sort of deep dives and all the consultancy work that we do as well, looking at how you make these decisions and how you mitigate the risks involved. So looking at some of the questions we've had, firstly, so we will be posting, as I said, the slides. They'll probably go up tomorrow, and the recording should be up by Monday. Couple of questions here on the early slides. So is the global CAM market share by units sold or by CAM demand, taking into account battery pack size? That CAM market share is by estimated production. Production is added up on a bottom-up production basis. And obviously, when we're looking into demand, we do take into account pack size as well. Question here on lithium manganese rich cathodes. Obviously seen an announcement recently by both Ford and GM going for that high manganese option, for GM as a sort of mid-tier cathode, and for Ford be closer to its top tier cathode. We include that under ternary cathode So we have a sort of 370 type thing that we put in our numbers. Probably worth pointing out that we're seeing a bit of a resurgence in that high manganese ternary cathode or high manganese cathode at the moment. Um, I think that's again because you can reach the sort of energy densities, but you can have a more resilient supply chain if you can get the manganese units, which at the moment very heavily dominated by China for high purity manganese of any type. You've only really got two producers outside of China who can produce into that supply chain at the moment. It's a big risk there. Um, and yeah, a few people sort of coming back from high nickel as well. Richard, I don't know if you had any comments on the manganese side of the market um, to put you on
No,
the
thanks.
spot.
I think you
That's all right.
covered it.
Okay. Well, actually, sticking with manganese, I guess. Next question: is there such a thing as high compaction LMFP, or has Gen 4 LFP killed lithium-ion manganese phosphate development? And I think I sort of alluded to that a bit that you know capex investment, particularly high capex investment, has slowed down because of the um, low margin environment, and that's probably meant we've had more of these incremental investments and changes. And obviously the higher densities that we're seeing with Gen 4 versus Gen 3 does show that that's continuing, which is something that us and others have predicted some time. But yeah, Richard, anything to add on that?
I'll just mention that there's a parallel technology restriction for LMFP in from China, so that there are compaction density data there for that, and I didn't, for the sake of brevity, I didn't cover all that today to keep it short, but there is quite a bit of information out there about that, and maybe that's a whole nother webinar.
So question here, it does lithium carbonate or battery grade lithium carbonate remain the source for Gen 4? I mentioned at the beginning we're seeing some Chinese refineries being asked more and more for lithium dihydrogen phosphate as a feedstock. I saw Richard on your slide, you mentioned both carbonate and hydroxide, actually.
Yeah, depends on the route you go. There's a lot of options there. It could be both. So it's a matter of cost and capability of your process. So it's I think either one is possible.
Am I right? It also impacts the environmental side of things with ammonia and things like this, or am I?
Yeah, no, that's right. The iron oxalate route, as for Gen less than 4, if you will, has quite a issue with ammonia restrictions. A lot of ammonium dihydrogen phosphate is used with your carbonate or hydroxide. And that ammonia is an emission that is a part of that process that you have to scrub. What you're discussing is moves that ammonia emission potentially elsewhere, right? It's not at the CAM manufacturer now; it's at the raw material manufacturer.
Yeah. Cool. And so just as the rise of LFP shifted lithium's primary feedstock to carbonate, yeah. So are we going so same question really? Are we going to see the dominant form of which lithium is commercialized? And I'll take that one. I mean, I think what we're seeing at the moment is a huge increase in intermediate lithium project products, and they can be, just a little bit processed, such as your sulfates. We're seeing more chlorides coming onto the market, which used to be a very sort of niche tonnage, as it were, going into the battery sector. You're seeing a lot more technical grade carbonates, and then you're seeing folks who are just producing the battery grade chemicals. And again, what they're being asked for is changing. So you're seeing, more of these, dihydrogen phosphates being asked for, not necessarily being to be delivered, but being asked for at least for Chinese refineries. You've then also got a lot of recycled feedstocks coming into the supply chain. Now, it gets incredibly confusing because we're going to end up, rather than just looking at this binary, okay, we've got brine, hard rock, maybe spodumene and lepidolite, And then we've got carbonate and hydroxide. I mean, it's always been a little bit more complicated than that. And if anything, it's getting even more complicated. I think that one of the important things is that, we still talk about the market in terms of LCE and lithium carbonate equivalent, and the vast majority of pricing is still priced off of the lithium carbonate price, CIF China or China domestic. So, we're probably still going to be talking in those terms, and that's what the sort of general conversations around the industry will be. But you will then have these formulas which just link prices, and the same way that you have different definitions of battery grade materials, you have different definitions of feedstocks as well. So does China's Gen 4 technology export restriction mean that Gen 4 CAM can still be exported, or is it the only technology? Or is it any technology that cannot be exported? Great question.
Uh,
Um,
my reading of the restriction is that it's the technology, not so much that, as I mentioned in my last slide, that you can buy according to what my understanding of that restriction. So there's a lot more people, probably experts in it than I am, but my understanding is you would be able to buy the Gen 4 CAM and then fabricate your batteries outside of China.
yeah, that's my understanding as well. And that sort of fits with the Chinese policy of trying to be a provider to the world.
Yeah.
Um, you know, and I don't think it's something that you can necessarily, take the material and then reverse engineer the equipment or the IP. So, what we're likely to be seeing is just this material going into CAM, which is then filling up those big import deficiencies that I showed earlier on in the presentation. And yeah, China will maintain a dominant position then. And the more dominant position you maintain, the more R&D budget that you can put in and maintain that going forward. Um, a couple more questions here, which were a bit sort of repetitious, looking at what we are doing in terms of intermediates and feedstock. I think we've covered that, at least up to my ability anyway. Um, okay, another question. Would it be possible to go through regional value content of 65% in battery cells in the EU with such a deficit of CAM produced locally? So this is looking at things like the Critical Raw Materials Act, which sets a target for domestic production. There are various other domestic content rules when it comes to automotive access. So, for example, the UK, if it wants to export to the EU, needs to have a certain amount of domestic content. Given that the battery is the most expensive part of the car and the CAM's most expensive part of the battery, it certainly makes it very difficult to reach those content requirements if you're importing Chinese CAM. So I think that's going to be very challenging. It's probably not impossible. Obviously, that partly depends on how much you're paying for the CAM. And yeah, as I say, I think it's part of that calculus that you have to do. And the big issue there is are you dealing with a legislation that has teeth or doesn't have teeth? In the US, a lot of the restrictions on domestic content and requirements like that do actually come linked to access to tax credits, or it's just a flat out no, you can't do this. Whereas in the EU, it tends to be more of a suggestion. So it's a bit more, this is what we're telling you to do. Can you please do it? Rather than having a big stick saying, if you don't do it, we're gonna fine you, or take away your tax credits. Richard, anything you wanted to add on that one?
That's fine. You covered very succinctly.
Great. Um, then how long do we estimate that it will take to develop this fourth generation supply chain in the West? Let's expand that question a little bit on, can the West, keep up with the level of technological development that we've seen in China? As we showed earlier on, we expect China to keep, over 75% of this supply chain within its companies. whether they're domestically located or not. Are we going to have champions, that keep up, or are we going to be more niche? And Richard, just trying to get your opinion on that.
A lot of it will relate to the phosphate supply also. There's information coming out of China where they're finding some limitations in their phosphate supply in various publications. So there's going to be a lot to the phosphate supply in order to move anything outside of China. If your two phosphate chemicals mentioned here are both the high purity phosphoric acid that comes from a different process than a thermal process than the ammonium dihydrogen phosphate that was also mentioned. There's more that's more of a Western provided material. So to move this outside of China is going to be more related to the phosphate supply, I believe, than it will be related to anything else.
Yeah. And then I just had a question, thinking about the potential patent barrier from Tesla. And, I mean, it's not really to single them out, but, we've seen a lot of moves to potentially cut out Chinese competition in the US, whether that be from vehicle operating systems, from direct Chinese investments, etc. And, I guess the sort of worry there is, and it sort of goes back a little bit to the last question as well, is, does the US just start falling behind from a technology perspective? Is it sort of cutting off your nose to spite your face, by not necessarily supporting a lot of these industries, and with the sort of defunding of a lot of the subsidies that the Department of Energy were handing out, I think it's very difficult for the equity and debt to be raised in these supply chains at the moment. So yeah, interesting to see what happens there. Again, Richard, I don't know what your personal opinion is. Would you rather have access to your communist technology, or or sit at home with your gas guzzler?
Well, you can discuss a lot of things about that. There are a lot of reasons to get a process patent. Process patents, my experience, quite good at basically guaranteeing your own freedom to operate. In other words, I've got a patent. I'm following this patent. Nobody can come in and say don't have freedom to operate. Another reason could be that if you're licensing technology, that impacts that impacts the value of the technology you're licensing. If you own the patent, a patent that limits that technology in some way, so it's a leverage point, if you will. So very hard to very hard. I've really only got one or two examples in my mind where someone defended a process patent against a competitor, but they are very useful for not only giving your own company freedom to operate, but also as leverage in these other types of situations.
Great. We'll just do two more questions quickly. One, I think we might come forward. Just one for you, Richard. Is high compaction density LMFP possible? Should we be watching out for that as well?
Yes, as I mentioned, there is a technology export restriction on that. So
Yeah.
the answer is yes. In fact, as I mentioned, the export restrictions give you a pretty good idea of what the suppliers have agreed to with the government as being key issues to be controlled and restricted. So there is a parallel example to that for the LMFP that can be found. It's not secret. It's out there. You can find it, and then we can have a discussion about that if you like.
Great. And then finally, just a quick question here on the EU PCAM dilemma slide. Are you forecasting a surge in supply versus demand in Europe? Am I reading it correctly? So just to go back to that one quickly. So effectively, it's worth. Oh yeah, it's a bit of mislabeling actually. So yeah, what we're forecasting is a big increase in demand, whereas supply doesn't necessarily keep up. So yeah, you're right, that is mislabeled. Thank you. Nice one to end on there. Richard, thanks so much for joining us. If anybody has any follow-up questions, you can find Richard's details on the slides earlier, and obviously our contact details as well. Feel free to reach out with any questions, and thank you for joining us.
Thank you. Thank you, Andy.
Thanks all.